Hello. In this video, we are going to derive the sigma molecular orbitals of water using group theory. Recall that water has this particular structure. It belongs to the point group C2V. If we draw it as a planar compound in the plane of the whiteboard, this particular axis is the x-axis. Up and down is the z or z axis, and the y-axis is perpendicular to the whiteboard. For water, we can divide the atoms into the central atom, which is oxygen, and the two outer atoms, the hydrogen atoms. And when we derive the sigma orbitals, we're first going to look at the linear combinations of the hydrogen atoms, which we sometimes call the group orbitals, that we will find under the point group C2V. We can label these 1s orbitals on hydrogen as S1, and this one we will call S2 for sigma 1 and sigma 2. Next, we make a chart which shows all of the symmetry operations of the group, the classes. So we have E, C2, sigma V in the XZ plane, and the last class is sigma V for the YZ plane. Our plan here is to form a reducible representation for the group orbitals that we find on the hydrogens. So just as in the vibrational case, when the first line of our chart was gamma atoms that don't move, here we have orbitals that don't move. So we want to see under each of the classes of the point group how many of these two group orbitals are invariant. How many of them do not move. So under the E operation, the identity, we know that both of the orbitals stay in the same location. So we have two orbitals that don't move. Under the C2 operation, our C2 axis is along the Z axis. So a C2 operation would take S1 into S2 and S2 into S1. Since both of the orbitals move, none of them stays put, so there are 0 orbitals that don't move. For sigma V, we have a vertical mirror in the XZ plane, that is the plane of the whiteboard, and that reflects S1 into S1, S2 into S2, so both of the orbitals stay in the same position. So we put a character of 2 for this particular class, for this reducible representation. Last but not least, sigma V in the YZ plane, so that is the plane perpendicular to the whiteboard. That would reflect S1 into S2 and S2 into S1. Since neither of the two orbitals stays put, we put a character of 0 for this particular class in the reducible representation, gamma orbitals that don't move. Our next step is to reduce this reducible representation into a linear combination of irreducible representations. One key step in the reduction formula is noting how many operations are in each class of the point group. In the case of C2V, each operation is its own class. So there's one operation in each class. So to remind us of this, we're just going to put a red number 1 in front of each symmetry operation in each class to remind us that there is one symmetry operation in each class. Next, we use our reduction formula to determine how many of each irreducible representation we find in the reducible representation. Recall that we start off with the first irreducible representation, which for C2V is A1. In the reduction formula, we divide by 1 over the order of the group, the number of operations in the group, which is 4 for C2b. So we start off with a 1/4. Then, for each of the classes in the point group, we first have the factor, the number of operations in the class, which is 1. Next, we have the character from the reducible representation, which is a 2, which we're denoting in blue. And the third factor is the character from the character table for the irreducible representation A1. And that character is a 1. For C2, the next class, there's 1 operation in the class, so we have a 1. The character from the reducible representation is a 0, so we have a 0. And the character from the character table for the irreducible representation A1 is a 1. For the third operation in the point group, we have 1 operation in the class, that's our 1. The character from the reducible representation is a 2, so we write our 2 in blue. And the character from the point group, the irreducible representation A1, the character is a 1. Last but not least, for the last class, there is 1 operation in the class, 1. The character from the reducible representation is a 0, and the character from the irreducible representation A1 is a 1. So we see that we have 2 plus 2 is 4, so 4 divided by 4 is equal to 1. So as there is 1 A1 inside the reducible representation, gamma orbs that don't move. Next, we want to see how many A2s are present. So again, we start with 1 over 4. The first class is E, so we have 1 operation in the class. The character from the reducible representation is a 2. And the character for the irreducible representation A2 is 1. For the next class, for C2, there's 1 operation in the class. The character from the reducible representation is 0, and the character from the irreducible representation is a 1. For the third class, the number of operations is 1. The character from the reducible representation is a 2, and the character from the irreducible representation is a -1 for A2. For the fourth and final class, there is 1 operation in the class. The character from the reducible representation is a 0, and the character from the irreducible representation is a -1. So we have 2 minus 2, which is 0, shows there are 0 A2s in the reducible representation, gamma orbs that don't move. The third irreducible representation in the class is B1, 1/4. So again, for E, there's 1 operation in the class. The character from the reducible representation is a 2, and the character from the character table for C2b is a +1. For C2, there's 1 operation in the class. The character from the reducible representation is a 0. The character from the irreducible representation is a -1. For sigma v x z, there is 1 operation in the class. The character from the reducible representation is a 2. And the character from the character table for the irreducible representation B1 is a positive 1. For the final class, there is one operation in the class. The character from the reducible representation is a 0. And the character from the character table for the irreducible representation, B1, is a -1. So we have 2 plus 2 is 4. 4 divided by 4 is equal to 1. So we have 1B1 included in the reducible representation, gamma orbs that don't move. Last but not least, our last irreducible representation is B2. And we will do this one relatively quickly. Recall that the first character is from the number of operations in the class. The character for the irreducible representation B2 is a +1. The character for the irreducible representation for B2 is -1 here. The character for the irreducible representation B2 for the third class is a -1 here. And the character for the irreducible representation is equal to a +1 for the final class. So here we have 2 minus 2, which is 0. So there are 0 B2s. So overall, our gamma for the orbitals, written as a linear combination, is equal to A1 plus B1. In C2V, we actually can see more clearly what it really means when we say that we can reduce this reducible representation into a linear combination of irreducible representations in this particular case. Because if we write down the characters for A1, each of the characters is a +1. If we write down the characters for B1, we notice that the characters are 1, -1, 1, and -1. So when we say that we can reduce gamma of the orbitals to A1 plus B1, notice what happens if we add column by column the characters. So if we add 1A1 and 1B1, I add the characters 1 plus 1, I get the same character that I had for the reducible representation. I get the character of 2. If I add together under the C2 class, 1 minus 1 is 0, which is exactly the character that we had. For sigma v x z, the character for A1 and the character for B1 are each positive 1s. We add them together, we get 2. For sigma v y z, the characters are 1 and -1. Added together, we get the character of 0. So here we can see quite clearly if we add together two irreducible representations, we add them character by character for a given class, we actually get the exact same characters that we had for the reducible representation, gamma orbitals that don't move. Our next step is to see what these actual group orbital linear combinations actually look like. Similar to the case that we did for vibrations using the projection operator method, we look at one typical group orbital, sigma 1 here, S1, and we want to see what happens to this particular orbital under each of the symmetry operations of the class. So here, each symmetry operation in the point group gets its own column. So under the identity, S1 stays exactly as S1. Under C2, C2 transforms S1 into S2. Sigma V is the plane of the board. It takes S1 into S1. And sigma V, YZ, takes S1 into S2. Now to see what these particular combinations look like, we need the characters from the character table for the irreducible representations A1 first, and then for B1. The characters for A1 are all 1s because A1 is the totally symmetric representation. So, as a result, we multiply the character from the second row times the term in the first row. So we have S1 plus S2 plus S1 plus S2, and this can be reduced down to S1 plus S2. And we can interpret positive numbers. The coefficients for S1 and S2 are each positive, which means that S1 and S2 have the same phase. So a shorthand way of writing that is simply writing each of the s orbitals, the 1s orbitals on hydrogen, simply as open circles. So this is the A1 combination. Now for B1, we need the characters from the character table for B1. In this case, the characters are 1, minus 1, plus 1, and minus 1. Again, we multiply the characters in this row times the terms in the first row, which gives us S1 minus S2 plus S1 minus S2, which again can be reduced in lowest terms to S1 minus S2. So in this case, S1 and S2, having different signs for their coefficient, tells us that these are different phases. And we often draw this as one open circle and one closed circle. So this shows that the phases of the s orbitals on the hydrogen atoms in the B1 case are opposite to each other. We have therefore derived both of the linear combinations of the group orbitals of the 1s orbitals on the hydrogen atoms by group theory, and we saw that there's an A1 combination and a B1 combination. Our last step is to determine which atomic orbitals on the oxygen have proper symmetry to combine with the group orbitals on the hydrogen. So let's look at the A1 case first. So here we have two hydrogen atoms that each have the same phase, A1. Now one of the combinations of atomic orbitals on oxygen that will have the proper symmetry to combine with the group orbitals is the pz orbital on oxygen. So this is the pz orbital on oxygen. And we notice we have positive phase, positive phase, positive phase. So this is bonding orbital in this direction, bonding orbital in this direction. So this is an all bonding combination for oxygen with the hydrogen orbitals. Now for B1, we need a combination where on one side the hydrogen atom has positive phase, but on the other side it has negative phase. So the proper atomic orbital on oxygen that has the proper symmetry would be a p orbital with a positive lobe to the left and a negative lobe to the right. I draw a p orbital there. So using the axes that we define here, this is the oxygen px orbital. So notice on the left-hand side that the p orbital has a positive phase and the hydrogen has positive phase, so that's bonding there. And then on the right-hand side, this hydrogen orbital has negative phase, the px orbital has negative phase. So this is also a bonding interaction. So we have A1 and B1. So we use two of the oxygen atomic orbitals to combine with the group orbitals on hydrogen. But what about the other two oxygen atomic orbitals? So we know that these are from the 2px and 2py, 2px. There must also be a 2py orbital on oxygen and there also must be a 2s orbital on oxygen. And one thing which might be a source of confusion is if we drew the 2s orbital on oxygen, it would also have the proper symmetry to combine with the group orbitals on hydrogen. We know from experimental and theoretical studies that the 2s orbital on oxygen is too low in energy to combine. So it has the right symmetry, but it doesn't have the correct energy to interact as strongly with the A1 combination of hydrogen atomic orbitals as does the 2pz orbital on oxygen. There is an important feature of the B1 orbital that we notice that between the hydrogen and the other hydrogen that we have a change of phase. So we notice that we have a positive interaction on the left-hand side and a negative interaction on the right-hand side. And the dividing point goes right through the node in the 2px orbital. So we see that the molecular orbital B1 actually has a node. It has a region where it goes from a positive phase to a negative phase going through 0. Whereas in the binding interaction we have for A1, we have positive phase, positive, positive phase. In the area where the three atoms interact, there are no nodes. So A1 has no nodes, B1 has one node. And as a general rule, the more nodes in the molecular orbital, the higher in energy the molecular orbital will be, just as in general, when we're talking about atomic orbitals, the more nodes an atomic orbital has, the higher in energy it's going to be. Our last step is to sketch out a qualitative energy diagram for the molecular orbitals of water. So we know that the lowest energy, the all bonding combination with no nodes, is going to have A1 symmetry. The next highest energy combination is going to be the B1 combination because it has one node. So we can put the bonding orbitals in order by the number of nodes. We also know that there are two atomic orbitals on oxygen that do not form molecular orbitals. So we have the 2s orbital on oxygen. It's from oxygen. And then we have the oxygen 2py orbital. And this will be higher in energy because we know 2p orbitals for a given atom are going to be higher in energy than for 2s, so long as we're not talking about hydrogen itself. Our last step is to realize that we have 8 valence electrons in water, and we can allocate those 8 electrons. So the first 2 electrons go into the lowest energy molecular orbital, A1. The next 2 electrons go into the bonding orbital with B1 symmetry. Electrons 5 and 6 go into an oxygen atomic orbital, 2s, which counts as one of the lone pairs on oxygen. So when we draw a Lewis structure of water, one of the lone pairs actually represents an atomic orbital on oxygen that has 2 electrons. And the last 2 electrons go into a 2py orbital, which is another lone pair on oxygen. In the process, we notice that each of the molecular orbitals of water has a different energy. It is non-degenerate. And that is entirely in keeping with our knowledge of the point group C2V. Since C2V has a high order rotation axis that is a C2, and not a C3 or higher, we know that there can be no degeneracy in water. Therefore, each of the molecular orbitals will have a distinct and different energy. I thank you very much for your attention. Have a good one.